Greetings to the pinacol rearrangement. Let's see how big we can get this. Too big. All right. We have a vicinal diol in both examples. I'm starting with a symmetrical one here. That way we don't have to worry about which O gets protonated. And I protonate with sulfuric acid. What was the reason to do that again? Oh yeah, I need this to be a better leaving group. What's it doing? Oh yeah, it's leaving. Now I've got a cation adjacent to a carbon that has an OH. So it's already tertiary. You're saying to yourself, why bother rearranging? We don't rearrange to make a cation that's secondary from tertiary, do we? And that's a good question, because that's exactly what's going on here. We're taking a tertiary, rearranging to a secondary. But this is much more important. Much better or more important than hyperconjugation is the fact that this thing can resonate with the cation, and this has full octets. Wasn't that the whole problem with carbocations? They have octet violations. This one doesn't. Why? Because it's on a carbon that has oxygen attached with lone pairs. So that's why this happens. Even though it's secondary, it's resonating. In fact, didn't we see something like this with allylic radicals and allylic cations? We said, oh, because of the resonance, we added 1.5 degrees to the degree sign, right? Can't we do the same thing here? Why don't you say roughly the same stability as 3.5 degrees because it can resonate? I can write that down. Resonance makes it about 1.5 degrees more stable than a normal non-resonating cation. And what happens is after this, you have an oxonium, and that's a strong acid, isn't it? So you get your catalyst back when sulfate ion, which you made way back here in the first step. Sulfate ion grabs a proton, and you make your carbonyl. Oh. This actual molecule here is called pinacol. They named this reaction after this specific example. It's called the pinacol rearrangement. The rearrangement step is here. This methyl moved. And we got that. Nice. Down here, I have a molecule that's not symmetrical anymore. I got rid of both the methyls here and put H's in their place. So now you have a choice of protonating an OH on a tertiary carbon or a primary. Remember what I said about unimolecular reactions being faster than bimolecular? Well, if you have a primary carbon with a leaving group, your only option is a bimolecular reaction. If you have a tertiary carbon with a leaving group, it's going to leave on its own. It doesn't need another molecule around. So it does just that, generating a tertiary cation, which could get better. You're saying, oh, it's resonating. So that's going to make it really nice. And then it resonates and you deprotonate at the end. Let me show you a shortcut that I accept on your test in these last 2 steps, which is really just the last step. Last step shortcut here. Last step shortcut. We got this thing here. And over here we have this thing. That's all we have. Yeah. And it's got a plus. This is a rearrangements happened already to get to these points. Rearrangement happened. You're resonating and then deprotonating. Remember, resonance is part of a molecule's makeup. You can combine a reaction step with a resonance step. So why don't you say, this thing's going to grab the H, and you get your pi bond, and that takes you from here straight to the final product. Isn't that nice? Similar story here. Deprotonate and get your elimination going on. Right there. So you don't have to draw this oxonium at all. And that's good for me, if it's good for you. We're going to finish with a nice practice example that's got many products. I think we got a blank page 11. I vaguely remember creating it. That's good. I need a blank page. And let's do something like this. A little square on there. Yeah. Okay, sure. I'm gonna use hots and heat. Hot. And we'll get 3 products. You can get 4 if you want. You can have this one. We can have, let's see, cation here, H moved. We got that. Sorry, I'm talking to myself as we go here. Should have had this worked out ahead of time. Shame on me. Cation here, instead of moving an H, I could move this carbon. Oh, that would be bad. Okay, I don't know if this is a great example to start with. Oh, it is a great example. How about just 2 products? I don't know how to draw it. Doing my best. I need to work on that one during the mechanism. I confess, I don't see it, not seeing it. There will be a product there when I'm done. I promise. And we'll put it here too. So we're gonna, which one do you want to protonate first? I want to protonate this one first. Why? Tertiary. Tertiary is going to be faster to make a cation than secondary. And it leaves. And we have a lovely cation here. Now that first product doesn't have this H, does it? First product, that H moves next door. And we're going to have very nice resonating cation here. And that's going to make our first product. What's going to grab that H? What's going to grab that H? Sulfate ion. Made that in the first step when you protonated your alcohol to make it a better leaving group. Grab H, make pi. Now I have to entertain the possibility of the other OH because I really want this ring to get bigger. Do you remember that cyclobutane has extreme torsional and angle strain? You remember that, don't you? So if I can somehow generate a cation here, then I can break this bond or this bond. That'll give two different products. Maybe I'll do 3 product in this reaction when I'm done. But to get there, I need to see the cations first. Whoa, I can't do that. Can I get my molecule? Close. I don't want that arrow. We'll get rid of it. Oh, I hit the, don't ever hit that button. 5, 4, 3, 2, 1, 5, 4, 3, 2, 1. Gotta wait for it to reappear, and my computer seems slow to, there it is. I gotta hit that button again. I'm one of those there days. What happened here? Okay. All because I hit the mouse arrow instead of this. I want to look at the products that would come from protonating the other O, because it seems to me that's where we can get our ring size to a better ring size. Generating this oxonium, which will leave. Generating this strained carbocation. Oh, there's an OH on there. These are the same. I'm hitting keys I shouldn't be hitting. Not even really in a hurry here. Okay, your 2 possible rearrangements that can make life better are what? There's only one. I can break this bond or this bond. If I break that top one, doesn't the ring get smaller? Ooh, I'm not breaking that bond. So I don't need this equal sign after all. But, in fact, I don't see a scenario where the 4 does get better. I don't see it. I picked a bad example. No scenario for ring expansion. Which is good. It makes our day a little shorter. There you go. I only have one there. C. Okay. Computer's saying the day should have been over a while ago. C, practice exams. for versions where cyclobutane goes to cyclopentane. And you'll see it on almost every exam. It just, I didn't think ahead to get a nice example for you. And I'm sure you're going to make me do one on review day. When's review day? Review day is Wednesday. And you're going to have email questions sent to me with practice problems. I will try my best to get the test one test 4. We're on 4 now. Test 4 outline ready by this evening, although I have appointments right after this, so your videos will be posted tonight. The outline will also be posted tonight. But some of you are pretty savvy students, and you kind of know what's going to happen. You're going to look through old exams. A lot of you have been doing this already, and it makes me happy. And you see, he's asked this same type of question 3 out of 5 times in the last 5 exams. I bet he's going to do it again. And usually you're right, aren't you? So, yeah, we have multiple old exams with answer keys. And I hope that's not news to anybody. Most organic chemistry classes aren't giving you all those old exams to study, but that was the thing that I found most helpful, was the students that had a club that got teachers to get old exams and made up their own answer keys. And that's how I learned organic chemistry, from old exams. So I decided I would have that ready for the students, so the good students could take advantage of that from day one. So look for some practice exams for versions where cyclobutane becomes cyclopentane and there's a vicinal diol and a strong acid and heat. I don't think you'll have to look very hard. And that brings to a close dehydration of alcohols. If you do need another product, here it is. H2O was made here and here. Dehydration of vicinal diols gives carbonyl compounds, and normal alcohols gave alkenes. And that's a good spot to stop and get your review questions ready for Wednesday. And I'll see you then. Oh, I don't know what happened. Trying.